All right, hey everybody, this is worksheet number 6 here on magnetic force and field. So I'm going to start off by explaining the equations and then we'll proceed just into the worksheet. This one shouldn't take that long. So as we've learned, there's a few right-hand rules. I think there's 4 altogether, but let's just worry about the 2 that we know so far. And that's the ones we have here, right? The right-hand rule number 1 and number 2. So, with right-hand rule number 1, it's this whole situation where you can find the direction of the velocity, the force, or the field, right? Just by setting up our fingers. And then we have right-hand rule number 2. And just going forward, I will be calling them right-hand rule number 2 and right-hand rule number 3. We have the one where we have a long wire, right? And through that wire, we have a current. And we're asked, what is the direction of the magnetic field due to that wire? That sort of tells us we're going to be using the right-hand rule number 2. So in that case, we set our thumb equal to the direction of current. So let's imagine that this eraser is a current that's going upwards. So it's going up this way. I put my thumb in the direction it's going, and then my fingers curl this way. So where my face is right now, the field's going into the page. And then you'll see if I curl all the way around, it'll be coming out this side here. And then coming out where these fingers are, it's coming out of the page. So relative to the side of the wire, it'll be going in or coming out. So on this side, it's coming out. And then on this side, it's going in. Okay. Sorry, that's probably the worst demonstration you've ever seen, but I think it gets the point across. Let's go through the equations here. So now we have equation number 2, which is the magnetic field produced by a current I through a straight long wire. So that's when we'll apply that. We next have the force on a charged particle moving in a magnetic field. We have the magnetic field of a point charge equation. And we have the magnetic force on a wire. The only thing I want to talk about here is with these 2 equations 4 and 6 here, we can see they're actually in this one for that matter, they're all cross product equations, which basically just means it's vectors in 3D space. And how we treat that is we just consider that cross as a sine theta value, where that theta is the angle between the direction it's moving and that magnetic field. Oftentimes it's equal to 90, right? And what's sine 90 is equal to 1. So most of the time it's sine 91. We don't really worry about it, but in certain occasions it can come up. And this is in opposite basically to what a dot product is, which is 2 variables with a dot in between them, and then that just tells us it's the cosine between the cosine angle between those positions. But I'll call it out when it's important. It's just kind of relevant to acknowledge there. Okay, so let's just jump into question number 1 here. And there's not much for me to write out on the board here. It's more to just explain my process, and I'll tell you how I do everything. So we want to first determine the direction of the force on a negative charge for the cases shown below. So with a negative charge, we take what the direction the right-hand rule tells us, and we just flip it, right? So with respect to number 1, I'm going to stand this way so you can see, on this side of my hand, where my watch is, that hand is the side, this is where the paper is, and on this side is coming out of the paper. Okay, so on number 1, part A here, we have, our middle finger, our middle finger pointing into the page. Our velocity here is pointing eastward, and my thumb is pointing up. Okay, but since it's a negative, we flip that. Our thumb's pointing up, so the force is in fact going down. And then moving to what's it called? Part B here, we have our middle finger my middle finger pointing down. We have my pointer finger for velocity going into the page, and my thumb is pointing westward or left. So the force is going to the right. We continue on here to part C. So C, we have the field. Oh, wait. Yeah, the field's going up. The velocity is going to the right, and my thumb is pointing out of the page. Therefore, since it's a negative, it's going into the page, right? We just flip it. Let's move to part D now. We have my middle finger coming out of the page, my velocity going down. So my thumb is pointing, here my thumb is pointing to the left. Therefore, it points to the right because it's a negative charge. And lastly, we have the field pointing leftward, the velocity pointing out of the page. Oh, I guess out is this way. Wait, which way did I say is out? No, this way is out. It's pointing out of the page, and my thumb is pointing down. Okay, so remember the page is what's on this side, right? Where my phone is here. I just can't really see, but going like that. And my thumb is pointing down, therefore the force is up. The last one is, you see we have the B field going up and V going straight down. Trick question, you can't do the right-hand rule like this, it breaks it, because they're not perpendicular to each other. And remember, what's sine with these equations here, it's a cross product. It's that V cross B. What's sine 180 is equal to 0. So there is no force here. When they're pointing in the opposite directions from each other, it's equal to 0. So what you can think about is, in reality, the angle between this B vector and this V vector is always 90, right? Even when it's going into the page and going right, like if you look at the angle that's like right here is 90 degrees. Okay, so when it's 180, you don't consider it. Okay, there we go. So no force for F. Let me pause the recording real quick and take questions. All right, so now we're back with number 2 here. And here we have a situation where we have 3 thin wires placed at the corners of this right triangle as shown in the figure. We're given the currents and we want to determine the magnetic field at that point P, right? So which right-hand rule should we use? You know, we're working with long wires. We want to find the field at these certain points. It's going to be the right-hand rule number 2, right? Where our thumb is in the direction of current and our fingers curl the direction of the magnetic field. So we're looking at that position P. The first thing I would like to do with these type of questions is establish the shortest distance between the wires, you know, 1, 2, and 3, and that position P. So I'm going to do a little dotted line, and this represents the shortest distance between them, which, you know, by definition is a straight line. So I draw in my straight line here. And I'll call this R3. You know, we know what these sides are. What is this? Actually, I should call this R1. This current one. So let's call that R1. Let's call that R2. And let's call that R3. Okay? R3 is given as 0.08 meters. I wonder if you guys, it's too small, huh? 0.08 meters. That's better. R2 is given as 0.04 meters. And R1, we need to find. How do we find R1? Well, that's just going to be, you know, R1 is equal to square root of R2 squared plus R3 squared, where R1 is equal to 0.089. Okay, meters. So now we know what R1, R2, and R3 are. Okay. Oh, this is going to get messy here. Let me erase these values here, because otherwise it's going to get so messy. But you know, it's all given. It's all given to you, so you know what they are. You know what R1, R2, and R3. Okay. So the next thing we need to do is find the field at all these different positions. How do we find the field? Remember, we have to use right-hand rule number 2. What I like to do is first, I'm going to start with I1. I establish the direction the current is going. This current is a dot here, so it's coming out of the page. So my thumb is pointing out of the page, out of the blackboard, right? The next thing I do is I trace the shortest distance from this current to that position. So it's that straight line. And I put my hand at the position. I then extend my fingers such that they are perpendicular to that straight line. Perpendicular means at a 90-degree angle. So my thumb is pointing out, my fingers are as such, and the vector is perpendicular to this line. So it's pointing up like this. Let's call that B1. Uh-oh. Let's do that. B1. All right. So sorry, guys. I know the iPad stopped working again, so that was great for me today. All right, and then now we can go on to I2. We now have our thumb going into the page. I trace to that point of interest. I put my fingers pointing down and I look at and I make sure the vector is perpendicular to the line, 90 degrees. So like this, that tells me that B2 is pointing straight downwards. B2. Again, I go looking at this position. My thumb is pointing out. I trace the shortest distance, that's that straight line, extend my fingers, and my vector is perpendicular to that straight line right here, to R3, right? It's pointing directly leftward. So I'm going to call that B3. The important thing here is that I'm saying it's perpendicular. The B vector is perpendicular relative to my, my thumb's, the direction of my thumb and the fingers, right? And that's important to remember because like you're doing the right-hand rule and it could be like, is it like this? Is it like this? Is it like this? It's perpendicular. It's whatever makes that 90-degree angle between the B vector and the shortest distance between them, which is a straight line. It's always going to be a straight line as the shortest distance. It'll be that right angle, right? So there's so many right angles in here. The next thing I need to do is, recognize like, how am I going to solve this? What am I looking for? I'm looking for B net. B net is equal to B net X plus B net Y squared. Both of them squared under square root. That should be familiar. And we just set up a coordinate system. Now this should be all familiar now. And Y. Okay, so I have my X and Y coordinate system set up. Now, why did I set it up particularly in this direction is because I have nothing in the positive, typically like the X points rightward, right? But here I have no vector pointing rightward. I like to work with my positives, so I make it point left. But I do know that this B1 has both components in the X and Y direction. So what do I have to do here is I have to find those. I'm going to call this angle right here theta, because that angle's theta, this angle's theta. And I can find that angle theta by the, I just take tan theta. So tan theta is equal to 0.04 divided by 0.08. And theta is equal to 26.6 degrees. Okay, 26.6 degrees. So now I know that I have a B1X and a B1Y, where I'll say my B, I'm going to write it down here just because I'm really running out of room up there. I apologize. I'll just write it like this, right? So I have BX, which is equal to, the X component is touching that angle theta. So it's B cosine theta. And I have BY. It's opposite that angle theta. So it's B sine theta. All right. So sorry, I know we like to draw it all in the free body diagram, but here I kind of ran out of space. The first thing I'm going to do is solve for B net X. So if we look at all the vectors in the B net X direction, I have B3 and I have B cosine theta. So I should say B1 actually. B1 cosine theta. B1 sine theta right there. Okay, so I have B3 pointing in the plus X direction as defined by a coordinate system, plus B1 cosine theta also. So what's the equation for this B? It's mu naught, the current there, I3, divided by 2 pi, and then R3, plus mu naught, I1 over 2 pi R1, cosine theta. We know that angle. We can do some factoring out here. And what we'll have is mu naught 2 pi I3 over R3 plus I1 over R1 cosine theta. Okay. So now plug everything in, work everything out. What we're going to get here is 0.0004 zeros. Let's see. Yeah. So 4 zeros, 6, 5, and then units be there. All right. the next part we have to do is solve for B net Y. So I'll call this B net Y here. So let's see what makes up our B net Y. We have, B1, the Y component pointing straight upwards, so positive B1 sine theta, minus B2. B2 is pointing straight down, so equals B1 sine theta minus B2. And same setup. And then, it's mu naught I1 over 2 pi R1 sine theta minus mu naught I2 over 2 pi R2. Okay, just factor everything out. Same process as before. Okay, and then I2 over R2. That comes out as minus 0.00005 t. Okay, we have X and we have Y components. We can now solve for B net. So we can see that our X component is positive, so therefore it agrees with our coordinate system. Let's call that B net X. And our Y is negative, so it's the opposite as what we define as positive with our coordinate system. Let's call that B net Y, right? It's pointing straight down. Therefore, our actual B net is this hypotenuse here. We'll call that B net. And let's say the angle here is theta prime. We can solve for B net through that equation up there, B net X squared plus B net Y squared, all under a square root symbol there. And B net is equal to 0.00082 t. And that theta prime is equal to tan theta prime. And that's B net Y over B net X. So theta prime is 37.6 degrees. Okay, and you'll say 37.6 degrees, I don't know, below the positive x-axis, however you want to define it, right? So I'll say below plus x. All right. After you solve that one, give you a second to look at the whole thing. And I'm going to pause the recording. All right, let's resume with question number 3 here. And in this question, we have a particle with charge Q moving in a circular orbit and with a radius R and a constant magnetic field called, B, exit or whatever. We want to first determine the speed of the charged particle. So we're looking for that V value, right? So with this, with the fact this particle is rotating in a circle, where we know its velocity at one point, right? It's like tangential, but it's like infinitely tangential. So like the next position, it'll be slightly this way, and then slightly this way, and slightly this way. And there has to be, like the point I'm getting at is there has to be a force going inwards. Otherwise, this particle will just shoot in a straight line, right? That's expected. You can imagine if there wasn't this force, what's keeping this particle from going in this circle? It's that magnetic force. So here we need to do a modification on the right-hand rule number 1, where we know we have our thumb direction, and we have our middle, and we have our pointer finger direction velocity, and our middle finger. And our middle finger, I guess it's kind of hard to see, is pointing straight out of the page. And the only thing that tells me I can actually solve this way is per the fact this particle is rotating in a circle and something's holding it from shooting off in a straight line. So that tells me my force is pointing towards the center, velocity is straight down, middle finger is out. Therefore, I know the B field here is coming out of the page. Coming out of the page there. And what we're asked to solve for is V. How do we address these kind of questions? It should take us back to, what's it called? 135A, right? Newton's second law. Force equals the mass times acceleration. What kind of acceleration do we have here? It's centripetal acceleration. where if you recall, AC is equal to V squared over R. What's the force here? There's only one force. That one force is a magnetic force, FB. So if we clean this up, we can see that FB is equal to M V squared over R. So now, what's this FB equal to? That's on our first page here. It's equal to Q V cross B, right? I'm gonna, tell you right here that what's the angle between this B vector and this V? It's 90 degrees, right? One of them is sticking straight out of the page. Imagine like this chalk here is sticking straight out, and you can see that there's a 90-degree angle. So I'm just going to write QVB going forward because sine 90 is equal to 1. And on this side, we have MV squared over R. So one of these V's will cancel out. Nice. So now we have that variable we're looking for on one side. We just got to do some cleanup, some rearranging, and we'll find that V is equal to QBR over M, right? So that's what V is. And actually, if you knew like the motion of a charged particle in a uniform magnetic field, the actual equation for that, he actually gave you this, was RMVQB. And you just rearrange this. I mean, it gets you to the same equation, but that's like kind of the proof in recognizing centripetal acceleration there. So, whatever you want to do. All right, that's part A done. So now we can look at part B here, and we're asked to determine the magnetic field produced by a charged particle at the center of the circle. Okay, so at the center. To do this, we need to use that equation. What did I call it here? The magnetic field of a point charge, equation number 4. So now we want to find that magnetic field of the point charge. So we're going to say B. I'll do it over here. I'll do it over here. It's part B, right? Is equal to mu naught Q R pi R squared, and then times V, right? So we already know what that V is from before, so we can plug that in, and it becomes mu naught Q times Q B R divided by M, divided by 4 pi R squared, right? So these R's will cancel out. And we have one more R left. And we can simplify the equation as mu naught Q squared B, let's call that B1, right? This is B1 here, divided by 4 pi R is equal to B, let's call it B2. That's like what's inside. And it doesn't ask, but, oh, I'm missing a mass there, times mass. And it doesn't ask, but what is the direction of the field there? We'll know it's going to be going into the page, right? And that's just because now we're like looking at the inside. And it's per the same properties. Okay, so that one was just kind of a proof of concept there. I'm going to pause and take any questions. All right, and now we're back with the final question, number 4 here. So here we have a 2-wire situation, right? So we have a rectangular loop of wire is placed in the same plane as a long straight wire, as shown in the figure. The current through the straight wire is 3 amps, and the current through the rectangular loop is 5 amps. We want to determine the force on the rectangular loop. So what we're looking for is the force of this straight wire on this rectangular wire, right? The first thing I need to establish is the direction of the magnetic field. I need to use a right-hand rule. Which one? Right-hand rule number 2. I set my thumb in the direction of the current, like this way, and my fingers curl going into the page on this side of the wire, right? From like this point down, thumb like this, it's going into the page right here. So I'll say like this, right? That's the direction of the magnetic field. And I want to know the effect of that field on this rectangular loop. So now I do another right-hand rule, this time right-hand rule number 1, where my pointer finger is in the direction of the current, my middle finger is in the direction of the B field, and my thumb is the direction of the force. So with respect to the top of the loop, my thumb is pointing straight up. I'll call that F1. Okay. With respect to this side of the loop, my current's going straight down. Middle finger, I guess you can't see, middle finger is going into the page, and my thumb is pointing to the right. Like that, right? So I'm going to call this F2. It's pointing this way. Down here, I have pointer finger this way, middle finger going into the page, thumb's pointing straight down. The force here is going down. Call that F3. And lastly, same thing. Pointer finger, middle finger, thumb. I see that I'm pointing leftwards here. I'm going to call that F4. Kind of getting messy over there. Sorry. Now we can make the point of, okay, we establish our coordinate system, same business as usual. We set up our equation. F net is equal to F net x squared plus F net y squared, square root that. Okay. Now, if we look at F2 and F4, we can see that they are equal and opposite in every respect. Therefore, they cancel each other out. You don't even need to worry about solving for this F net x. It comes out to 0. Call it 0. And thus, we can cancel out that square root and that square, right? So now, what we can say is F net is equal to F net y. And the reason why, okay, these two are equal and opposite in every respect, they cancel each other out, but why are F3 and F1 doing that? And the explanation for that is within the equation that there's an R value, the distance from the straight wire to the relative face. The distance from up here to here is different than the distance from here to here. So they're not equal and opposite. Not like with F2 and F4. No, we have to consider them and independently solve for them. And if we look at all the forces in the y direction, we'll see that we have F1 pointing upwards, so it's positive, and we have F3 pointing downwards, so it's negative. So F1 minus F3. And now comes the fun part of expanding this equation. So I can get for F1, I'll say is equal to, I1, it's that straight wire. Oh, I'm sorry, no. So F1 is equal to the current that's going through the rectangular loop. So I2, that length that we have, and then cross product B. But for both cases, they're equal to sine 90, so equals to 1, right? And then minus, again, I2 LB3. So the difference between them in respect to their magnitudes are within these magnetic field variables, right? We can factor out I2L leaving B1 minus B3. And I'm going to continue over on this side because I need the room. Okay, so we now have, it's equal to I2L. We have to expand these B variables, mu naught I1 divided by 2 pi R1 minus mu naught I1 divided by 2 pi R1. All right. So now it's kind of important here. We recognize where our currents are coming from, right? I2, this is the current that is within the rectangular loop. I1, that is the current that produces this magnetic field. That's why within these magnetic field variables, we use I1. So don't get those mixed up. It's very, very important there. And then you factor out what you can, I2 L mu naught divided by 2 pi. I'm not going to call this R1 here. Let's call this R3. Right? Those guys are actually different. And actually in I1, for that matter, we can factor that out. And then we're left with that factored out form, my 1 over R1 minus 1 over R3. R1 is this distance from the long wire to the top face. And then R3 is from here down here. And that's equal to 0.055. So now we have every variable we need. We can plug everything in and we can solve here. So I'm not going to write all of them because that's crazy and to take like forever on this blackboard. But I guess the important thing to realize is that this is all between the two variables. These are the same, and these two things are what's different. So make sure you factor out, otherwise it'll really take a long time. So if you plug everything in, what you're going to come out with is 0.00000. That's 5 zeros. And then 786 newtons. And what's the direction of the force? Well, I'll tell you, just because F1 is greater than F3, we know it's upwards, right? And how do I know it's greater than? Because within F1 is this variable B, right? Which can be expressed as such. The R1 here is much smaller than what R3 is here. Smaller in the denominator, the bigger the value actually is. So that's what tells me F1 is greater than F3. Therefore, I can say it's upwards. Okay, so that's equal to F net Y, which we already talked about, is what's equal to F net itself, right? There's no X component of F net. Okay, so pointing upwards. All right, that's that question. And that's our final question. And more updates on exam review to come. We'll address that when we get there. Thanks for watching this video. I'll take questions now on question number 4.